Hey everybody, welcome to Math 20-1 Quadratics Unit, Lesson 3. Today we're going to be looking at the standard form. Make sure you're ready to take notes, and if you need to pause the video to catch up, maybe send your teacher a question about something you see, please do so and then continue on. So let's start by looking at some of these quadratic functions in standard form. In standard form, we will have, and I'm just going to grab a little bit of a pen here. Y equals ax squared plus bx plus c, where a, b, and c are real numbers. A, under no circumstance can that equal 0, because if it's 0, that means our quadratic term disappears. But B and C, they can equal 0. So those two terms can be missing, or either one of them can be missing. So what we have here are 4 graphs with their corresponding equations below. It's asking us to state the y-intercept of each graph and compare the point to the function, and asking, what do we notice? Well, the first thing, let's get those y-intercepts with their ordered pair written in. Now you may notice that the y-coordinate of the ordered pair is equal to that c term or constant term at the end. Notice here we got 5 and 5, negative 3, subtract 3, 4 and 4, 4 and 4. Let's look at it again. Here it says, compare the function of the graphs that open upward. Well, the ones that open upward are these two right here. What do we notice about them? Well, looking at the equations, we notice that the x squared terms are positive. In this case, it's a positive 1 in front of both of the x squared terms. Well, let's look at the opposite of that. What about the ones that are downwards? What do we notice? Well, these are the two that are down. And we notice that if those things are negative, it opens down. So let's go and head into some more notes in our note package and summarize some things that we've learned from before, as well as things we just noticed about the standard form. So let's look at how the parameter of A affects the parabola. Well, like in vertex form, when A was less than 0, it opened down. So in other words, it looked like an upside down U. However, when A was greater than 0, the parabola opened up like a regular U. We also noticed that when A was between -1 and 1, in other words, when the absolute value of A equaled 1, that the parabola was actually wider than the graph of y equals x squared. And when A was less than 1 or A greater than 1, in other words, when the absolute value of A was greater than 1, we can write it both ways, that the parabola was actually narrower than the graph of y equals x squared. Note that this is exactly how A was affected in vertex form. Now, the parameter of B is a little bit different. Vertex form didn't have B. B, because it's that linear term, almost like mx in mx plus b, it tells us the slope of the parabola. In other words, kind of how fast it's rising or falling. But in Math 20-1, we aren't going to be using that information much, but it can be useful in certain applications. Now, what about parameter C? Well, that is what we just figured out in the activate section. We saw that parameter C was equal to the y-intercept. Note that the location of the vertex cannot be determined just by looking at it, in other words, inspection, at the equation in standard form, like we could do in vertex form. Remember, in vertex form, and I'll just write it out over here, y equals a times x minus p squared plus q. We could easily just pick out that vertex as p and q. We can't do that in this standard form. However, we can get the y-intercept, which is something we couldn't do in vertex form. However, in this standard form, the x-coordinate of the vertex can be found on your formula sheet using this lovely little equation. X equals negative b over 2a. And therefore, this would also be the equation of the axis of symmetry. And the formula sheet, let's look at it. It's linked here as well. And let's see if we look down. It's right here. I missed it. Axis of symmetry. So once you have the x-coordinate, we can substitute it into the function. In other words, we can say f of negative b over 2a, that's going to equal the y value. So let's look at an example here. This question says, use the quadratic function f of x equals negative x squared plus 6x minus 9 to answer the following questions and check by graphing. The first thing is, what direction of opening, in other words, concavity, is for the parabola? How do you know? Well, we know that when the a value is negative, this thing is going to open down. And this is just the case here. Even though we don't have it there, the a here equals negative 1. And the a is less than 0, which means this thing opens down. Well, what about the domain of the function? Well, all quadratic functions have a domain. Terrible, a looks like a 9. A. In interval notation, x is an element of the real numbers. Or in set notation, it was x is an element of the real numbers. And in interval notation, remember, we have to use round brackets with infinities on each end. It says state the coordinates of the y-intercept. Well, we remember the y-intercept can be written as 0 and c. Therefore, it is 0 and negative 9 because our c value is negative 9. It then asks, does the parabola have a max or a min? Well, we know it opens down, so we know it's going to be like this. So the vertex is going to be the maximum point. We know that for sure. Now, unlike in vertex form where we could figure out what is y, in this form as it is, we can't figure it out right away, but we will get to that in a minute. We can figure out the axis of symmetry because we have this lovely little equation, x equals negative b over 2a. So let's plug everything in. We know our b value is 6, and our a value is negative 1. Therefore, we always work vertically. Negative 6 divided by 2 times negative 1, which is negative 2, is a positive 3. So the axis of symmetry is x equal to 3. Well, what about the coordinates of the vertex? Well, we know now, because we know the axis of symmetry, we know that the coordinates of the vertex must be 3 with some value of y. So what we need to do, and we're just going to go over here where there's a little more room to work, we're going to say, what is the f of 3? Well, let's plug it in to our original quadratic function and say negative 3x squared plus 6 times 3 minus 9 is going to be the new y value. Well, 3 squared is 9, so that's negative 9 plus 18 minus 9. That's going to equal 0, which means the coordinates of the vertex are 3 and 0. And find another point that lies on the parabola. Well, we get to pick any point we want. Let's find f of 1. So in other words, when x equals 1, 1's a nice easy number. I like everything to be as easy as possible. Don't make things harder than necessary. So I have negative 1 squared plus 6 times negative 1 minus, oh, it's not negative 1, sorry, positive 1, minus 9. Well, because the 2 only applies to the 1, this is actually negative 1 plus 6 times 1 is 6 minus 9. And that is going to give us negative 4. So another point that lies on this graph is going to be 1 and negative 4. Now it asks us to check this by graphing. Let's get our calculator out. And we're going to put in our y equals and negative x squared. Notice I used the negative button plus 6x minus 9. Okay, let's graph it. There it is right there. Well, because it goes to the left and to the right, it's starting to get wider and wider to the left and wider to the right. We know that the domain is the real numbers. We can clearly see it opens downwards. It says, what is the value of the y-intercept? Well, to do that, we're going to use that second trace button, and we're going to hit 1 for value because we know the y-intercept is when x equals 0. So we just put in 0, hit that, and we get the negative 9, which is what we want. Just by looking at this for part D, we can see that it indeed does have a maximum. But we want to know, what is the axis of symmetry? Well, we can figure that out from this graph by using the maximum feature in second trace. So second trace, we're going to do number 4 for the maximum feature. We're going to go a little bit to the left, hit enter, then a little bit to the right of that maximum, hit enter. It's going to guess between those two arrows, which is what we want. And we see that the x value equals 3 when y equals 0. And we know for a vertex that the x coordinate is the axis of symmetry, and that's what we figured out right here. We also can see from our calculations we got 0, and that's what it's showing as well. Well, what about the point that we checked? Well, you could have checked a different point, and it's easy enough to figure that out. We're just going to go back to that value function. Second trace, 1 for value. We're going to put 1 in, and we get -4. Let's move on to question 2. I've kind of already went ahead and made this nice little graph here, because the question is asking us, state the y-intercept of each function as well as whether it opens downward, upward, has a maximum or a min, and whether it appears wider or narrower than the graph of y equals x squared. Let's start with the y-intercept. Let's call this A, B, and C, and let's look at A. Well, we know that the y-intercept is of the form 0 and c, so the y-intercept here is 0 and -24. Now b is a little different. We don't have this constant term tucked in on the end. What that means is actually we've added 0. So for the y-intercept of b, it's going to be 0 and 0. Now for c, the constant term is 8, so it's 0 and 8. What about concavity? Opening up or down? Well, we have to look at the a value. Remember, if a is greater than 1, it's up, opening up. And if a is less than, 0, it has to be positive. If a is negative, in other words, less than 0, it's down. So what do we have here? For part A, we have 3. Well, that's greater than 0, so it's up. For part B, well, that's a -1. A is less than 0, so it's down. What about for this one right here? If A is less than 0, again, it's down again because it's a -1. Now let's look at max and min. Well, that really is tied to the concavity. If it is opening upwards, like this one is, it's going to have a minimum. However, if it is opening down, like this one or this one, these two are going to be maximums. And what about the wider or narrower? Well, the wider or narrower depends on the absolute value of A. If the absolute value of A is less than 1, it's actually wider. But if the absolute value of A is greater than 1, it's narrower. That honestly is the word narrow, I promise. So in this one, we have 3. Well, 3 is greater than 1. Therefore, this is narrower. For this one, the absolute value of A, well, the A is a -1/2, and the absolute value of a -1/2 just equals a half, and that is less than 1, so this is wider. And the absolute value of -1, because that's the A value of C, that equals 1. Well, what happens when they're equal? Well, the wideness doesn't change. So in other words, it's the same as x squared. So now it's time for you to pause the video and open the practice document and give question 2A and B a try. I really would love for you to email me to let me know how it's going. It might be like I'm not sure how to do this yet, and that's okay. This is like a check-in just to tell me where you're at. Or it might be, hey, I got this, let's keep going. Whatever it is for you is okay. You could ask for help in your email, and I would definitely get back to you. Okay, so now let's look at question 3. It's asking us to consider k of x. Remember that it doesn't always have to be f of x. It can be any name. So here we have k of x. So k of x equals 2 times x plus 1 squared minus 8, and it's written here in vertex form. It's asking us to rewrite this in standard form. We've actually done this before. What we're going to do is we're just going to FOIL out that binomial that's squared and simplify. So k of x equals 2 times x plus 1 times x plus 1, oops, no longer squared. We got to remove like that. Let's take that away. There we go. And then we're going to subtract 8. Well, foiling that out, we're going to leave this 2, but we're going to FOIL this term with this term. So we get x squared plus x plus x plus 1 minus 8, which is 2 times x squared plus 2x plus 1 minus 8. We're going to distribute the 2 through that trinomial. Notice it only goes through the first 3 terms. The 8 is outside the bracket. Oops. 2 times 1 is not 4. 2 times 1 is 2. And now we're going to simplify it by combining the constants at the end there, and we get minus 6. Now the next part of the question is what is the value of A, B, and C? Because this is like a numeric response type question on an exam. But the thing we have to take care of is notice what they did here. They put a negative. And they did that knowing our answer would have that negative there. So we can actually add in the value that we have for C. It's not the typical C right here. Get rid of that. B equals 4. In this case, the C that they're talking about here is that positive value there. So answer would be 2, 4, and 6. It asks us, what characteristics of the graph can you determine from this form? Well, in this standard form, we can determine the concavity by looking at A. And from that, we can determine if it has a max or a min. We can also determine the y-intercept. Now, in the vertex form that they started with, we can also determine the concavity max and min in vertex form. But vertex form has one thing different. We can also determine the vertex. And from that, the axis of symmetry and the actual max-min value. So we can determine y equals right there. Okay, let's look at question 4. In this question, it is asking us to write the equation of the parabola in vertex form and convert to standard form. Well, remember in vertex form, we need to know the vertex. And in this case, the vertex is -1 and -1 and -4. Sorry, -1 and +1. I don't know what I was thinking there. So -1 and 1 because we go over 1, up 1. So we can start by saying y equals a times x minus p squared plus q, and fill in the p and the q. Remember, the p is the x value of the vertex, so it's x minus -1. We have to be very careful of that negative sign in the middle there. And then we're going to add the q, in this case is 1. And let's just simplify it a little bit. Say x plus 1 squared. The next thing we're going to do is find another point on the graph. Let's pick something easy. Let's pick 0 and 2. And we're going to substitute that x and y for the x and y in our vertex form to solve for a. So I'm going to put 2 here. I'm going to put 0 there. I'm going to simplify and solve. So that means 2 equals a times 0 plus 1 is 1. 1 squared is 1, so really it's like multiplying this by 1. Then we have that 1 on the end. We're going to subtract that from both sides. So in that case, a equals 1. This means that the equation in vertex form is y equals 1, we won't write it there, times x plus 1 squared plus 1. And let's expand that out. We get x plus 1 times x plus 1 plus 1. Lots of 1s. And we get x squared. This is actually going to be 2x plus 1 plus 1. And simplifying out by 2. If you want to make sure that you have this done correctly, definitely double check my foiling. If you ever find it that I have any mistakes, you definitely let me know. And there we go. So let's look at a different form that's really connected to the standard form and the vertex form, and that's the factored form. In a factored form, it can be written like this right here. Oops, that didn't go over where it will. There we go. And we say f of x equals a times x minus r times x minus f. Well, in this form, r and s are what's called the roots of the function. And all this means is they're the values of x where the graph of the function crosses the x-axis. Starting to sound like an x-intercept. But this form of the graph also gives us other useful information. As we mentioned, the roots are zeros, come on points x and r, so we know that one. This is something new that wasn't available to us in the other two forms. The vertex of this is the highest and lowest point on the graph, which is the tip of the parabola. Now, this form doesn't give this to us right out, but there is a process we can follow. The first thing we can do is find the midpoint between those two x-intercepts. Well, why is that important? Let's draw a little graph here so that we can see why that might be a good thing. Well, if we have this right here, and let's say we have a parabola kind of like that, where this is -3 and this is 1. Well, we know the vertex is here, and more importantly, we know that the axis of symmetry goes through that point. In other words, it's what cuts the parabola in half. This means this is equal distance, these two x-intercepts are equal distance from the axis of symmetry. In other words, this is the middle, and the middle is almost like the average. So we are taking the average of the two x-coordinates. So we're saying r plus s divided by 2. It's like on a test when you have two tests and you want to know the average. You add the two marks together and divide by 2. Well, we want to know the average of those roots, and that's going to give us this x value right here. Well, now that is going to give us an x value that we can plug back into our f of x to give us the y value. So there's a little bit of math involved. We can't look at it and see it. So in other words, we can't inspect it and see these values, but we can definitely look at it. Well, now that we know that average value, that's going to definitely help us find the axis of symmetry because that's just going to be equal to the average. Now, the concavity is just like same old, same old. Nothing new to see here. Move along, folks. If A is greater than 0, it opens up, and if A is less than 0, it opens down. Nothing new here. The y-intercept is a little bit new. We can't inspect it like we can in standard form, but we can do a quick calculation. In this particular one, A times R times S will give us y-intercept. So just like the other two forms had their advantages and disadvantages, this one does as well. So when we want to write something in factored form, if we're given the graph, we can identify the x-intercepts and a point, and we can use that to put it into factored form. And we'll do some examples. And if the equation is in standard or vertex form, we can simplify and factor it to get it into the factored form. So let's look at question 5. Match each graph to the one of the equations below and explain the strategies we use. Well, we have a lot of new information about these things in factored form. We know that if we have those intercepts, which in this case is at -3 and -1, we can say that this is f of x equals a times x minus -3 and x minus -1. So these have two negatives, which means we have a times x plus 3 and x plus 1. Well, what about this one here? Even though the general shape of it's different, it still has negative 3 and negative 1. So as general, I won't write all of the calculation part out, but this is going to look exactly the same. It's going to say x plus 3, a times x plus 3 times x plus 1. Now this one, a little different. These are both positive. So this one, to start with, is going to look like a times x minus 1 times x minus 3. Now notice when these are positive, these x-intercepts are positive, these here are subtracted, and when they're negative, they're added. Okay, keep that one in mind. Well, what about a value? What do we know about a? Well, we know that this a value is going to be less than 0 because it's opening down. Same with this one. This one's the opposite. This one has to be positive. Well, right off the bat, I see 2 here that could be this third one right here, this number 3. We have 2 possibilities, this one and this one. But we have to figure out in this one right here which one it is. We can go ahead and solve for a if we want, but one other point that might be useful is the y-intercept. The y-intercept here is 0 and 3. And we learned that if we wanted to find the y-coordinate, we can multiply a times r times s to get that one right there. Well, looking at this one, let's look at this one right here first. 2 times 1 times 3, well, that has a y-intercept of 6. But this y-intercept is 3, therefore, this third graph cannot be b, which means probably by the process of elimination, it's going to be this one. But let's just check. 1 times 3 is 3, and that's what this one tells us. The y-intercept should be 3. So this one is A. Now what about the other two? Well, we know it can't be A or B because they have the wrong factors. So it must be this one or this one. For this one right here, notice that this one is kind of higher. It's kind of narrower than this one right here. We also notice this one has a y-intercept of negative 6, and this one has a y-intercept of negative 3. So that one's negative 6 and negative 3. Well, let's look at what, for this one, what a times r times s is. For this one, we have negative 1 times r. Well, this r actually, remember, this is minus negative 1. So we have to say negative 1 here, times the s, which is minus 3. So this gives us negative 1 times negative 1 is positive 1, times negative 3 is negative 3, which means this one here is C, which means this one must be D, but you can check it by multiplying these numbers here. Negative 2 times negative 1 times negative 3 is negative 6, which is what we get. Well, let's look at some strategies for writing these quadratic functions in factored form. The first thing is identify the x-intercepts. So we are going to find where the parabola crosses the x-axis, and these points are the intercepts or roots, and we're going to say one of the roots is r and the other one is s. We are then going to write it in this factored form. but we need to find what the A is. We're going to use another point on the graph that we know, but not one of the x-intercepts. And this point should have coordinates x and y. We're going to substitute those back in to solve for A, and that new A, we're going to pop back in to the formula and rewrite it out in full. Okay, let's look at question 6. It asks us to determine the equation of the following in standard form: y equals ax squared plus bx plus c. Well, we can actually do this in two ways. We can do it by starting off in factored form or vertex form, but in this example, let's do factored form. Well, this one and this one are our zeros, and it says we need to determine those first. So this is r equals 1, and this is going to be s equals 3. So writing that out, y equals a times x minus 1 times x minus 3. Then we're going to get another point on the graph that's on one of the crosshairs, and a good one would be this vertex. That's at 2 and negative 3. And we're going to substitute those values into here. So we're going to put a negative 3 there for the y, and wherever there's an x, we're going to put a 2. 2 minus 1 times 2 minus 3. Well, what do we get? Nothing happens on the left-hand side, but on the right-hand side, we get 1 times 2 minus 3 is negative 1, which is really the same thing as saying negative 3 equals negative 1 times a. Dividing both sides by negative 1 leaves us with a equals to 3. So rewriting this out, we get y equals 3 times x minus 1 times x minus 3. Now let's FOIL it out. And remember, there's more than one way to do this question, so if you decided to do something a little bit different, that's okay. We're going to start next by foiling things out. Now, we might want to expand that this way first, but that's going to make things a little more difficult. So what we're going to do, we're going to FOIL out this one first here. So we're going to hold on to that 3. He's going to hang out in the front. And we're going to go x squared minus 3x minus x plus 4. Like that. And then we're going to distribute the 3 to get 3x squared minus 12x plus, oops, I wrote this as a 4. Let's fix that. That's negative 3. And then 3 times 3 is 9. And again, you could have started putting it vertex form first because you definitely know a vertex and another point, and then followed through. If you come up with a different way, let me know. So let's move on to question 7, and it says use the quadratic function f of x equals negative 3 times x minus 2 times x plus 5 to answer the following questions. Well, the first question, what is the direction of the opening? You guys are good at this by now. We know that this is negative, so a is less than 0, so it is going to open down. What about the domain? We know the domain of quadratic functions now. In interval notation, it is always going to be negative infinity to infinity, with the one stipulation if it is problem solving and we have to consider the context of the question. Well, what are the x-intercepts? Well, the x-intercepts come from the roots, and those come from x minus 2. When does that equal 0? And x plus 5, when does that equal 0? Well, that's when x equals 2, so that is one of the zeros. And this one is when x equals -5. And to write those as intercepts, it has to be an ordered pair. So that's going to be 0. My bad. Let's try that one more time. It's not going to be 0. It's going to be 2 and 0 because the y value has to be 0 for x-intercepts. And it has to be -5 and 0 right there. Well, what about the x-intercepts of the graph are sometimes zeros? Why do you think this is? Well, we kind of just talked about it. This is because the x-coordinate of the intercept makes f of that 0, f of x equal to 0. So if we take this 0 here, plop it into the function, we're going to get out 0. And you can actually try it. Go ahead. Put the x in here and put the 5 in here. And let me know what happens. What information is in the function tells you the parabola has a maximum? Again, we know this thing opens down from part A, therefore it must have a maximum right there. How could you determine the value of the maximum from the equation in this form? Well, remember, we are going to find the midpoint or the average. And to do that, we're going to use that R plus S divided by 2. In this case, our R value, we said was, well, let's look at it up here. Our value is 2, but our S value is -5 because this has to be written as minus 5. So if the R value equals 2, the S value equals -5, the midpoint is the average of those two, and that gives us -3/2, or as a decimal, -1.5. And this would be how we can determine the maximum. Because now that we have this, we can actually take that and plug it in, whatever it works out to be, and that's going to equal the y max. Now, we're not going to spend a ton of time talking about factoring methods other than a quick review. There are videos posted in the prerequisite skill page of the course website, and you can definitely go ahead and review that to remind yourself, how do we find the greatest common factor, difference of squares, and how can we factor a polynomial or trinomial when a does not equal 0, or when a equals 1, or when a does not equal 1. There's a bunch of different ones. Definitely check those out. Well, in this case right here, for greatest common factor, we are going to look for a common factor between all the terms, and that is what is going to be taken out. And I look at it in two ways. I not only look for the common factor of the variable, which in this case would be x, but I'm also going to look for the common factor of these coefficients. This one's a little tricky. It's actually a 2/3. This one might not be as evident, but we can take this negative 2/3 out, and we can make sure we're doing it right by foiling back in. So negative 2/3 over x times x is negative 2/3 x squared. And then negative 2/3 x times negative 2 would be positive 4 over 3. If you want to figure it out the other way, think about, well, if I'm taking out 2/3, that means I am taking 4 over 3 and I'm dividing it by negative 2 over 3. Little fraction work. I know we all love fractions. Flip and kiss. So we're going to flip the 2 over 3 and we're going to kiss them. In other words, multiply them. I don't like using x because it gets mixed up with a variable, so I'm going to use a dot. The 3's cancel, meaning I still have this negative, so we have negative 4 on the top, 2 on the bottom, which gives us negative 4 divided by 2, which is negative 2. Probably one of the harder ones you'll see, especially because of the fractions, but we're going to do more, so don't worry. The second one is the difference of squares. Remember, the difference of squares states that if we have a squared minus b squared, regardless of if a and b are coefficients, numbers, variables, or a combination, this is just going to equal a minus b, a plus b. For example, this is the same thing as saying 3x squared minus 4 squared. So our a is 3x, our b is 4, so we just say 3x plus 4 and 3x minus 4. Now for the trinomial factoring, there are many different methods. I use an X method, and that's described in the prerequisite skill page. This is kind of what it looks like. I won't go in through this right now, but basically you're looking for 4 times 9 equals the number on the top part of the x. The b value equals the number on the bottom part of the x. We're looking for two numbers that multiply to make 36, but add to make 15. Now you have to go through some of the factors of 36. I've landed on 3 and 12. I then take those two numbers and divide it by the a value, 4. I then reduce the fraction if possible. In this case, this becomes 3 over 1. This one stays as put. And then I do what's called bottoms up. Bottoms up. The 4 has the x come after it, and then I add the 3. The 1 has the x come after it, but it's a hint of 1, so I said 1x plus 3. And then that becomes x plus 3. And this is where these two factors come in using the x method. If this is not the method for you and you have something different, that's okay. You do what's best for you. And if you're having trouble, make sure you contact your teacher. Now, I won't go through question 8. These are in the notes, in the completed notes. They are factoring. Definitely you want to take some time to review those to make sure that you understand this factoring from Math 10C. So how could we find the axis of symmetry of the function without graphing? Well, looking way up, we can either, if it's in factored form, use x equals r plus f over 2, or looking even further up, we can use this if it's in standard form. So heading on back down, because it's in standard form, we're going to use x equals negative b over 2a. And I noticed in my completed notes that I have made a mistake. So if you're seeing those as you're looking at this, I will get that fixed at one point. So x equals negative b over 2a. Well, the b equals negative 2, and the a equals negative 1. So we're just going to plug and play. So we have negative of negative 2 over 2 times negative 1, which gives us positive 2 on the top, negative 2 on the bottom, which gives us negative 1, which means the axis of symmetry is negative 1. So again, I want you to give it a try. I want you to try some of the factoring, making sure you know how to do those, and I want you to check in with your teacher and let them know how you're feeling. Even if you're not feeling really good, let them know, and then that gives them the opportunity to help you. It's the finale, folks, and we're going to put everything together. We're going to look at 3 functions in 3 different forms, and we're going to figure out what characteristics can we identify with inspection alone. And remember, inspection is looking, not calculating. If there's anything that has to be calculated, we're just going to leave it blank. We're going to start with the first one, which is in vertex form. And let's see what we come up with here. In vertex form, we can see that the P is 2 and the Q is 8, so we can easily find that just by looking at it. We have a vertex of 2 and 8. We also know by the A value right here that it's negative, so it's going to open down. In other words, it's concave down. The axis of symmetry, well, we know that comes directly from the vertex. In this case, it's x equals 2. And we know that it's going to have a maximum because it's concave down or opens down, and its maximum is the y value of that vertex. We can't identify any zeros or y-intercepts, but we can definitely tell the domain because we have learned that the domain of these things, these quadratic functions, are always x is an element of the real numbers. And the range of this thing is always going to be from the minimum value to the maximum value. Well, the minimum value of this is negative infinity because remember, this is it's going to look like this. So it's going to start at the max and go down. So we're going to say the minimum value is negative infinity, which means in this interval notation, I'm going to say y is less than or equal to that maximum value of 8. And we always have to state the number system like that. There we go. Well, what about standard form? What can we figure out just by looking at it? Well, we definitely can't figure out the vertex, but we can figure out its opening down by looking at the A value, which is negative 0.5. We can't figure out the symmetry. We can figure out that there is a maximum point because we know it's concave down, but we actually can't figure out what that point is without doing calculations. And remember, this is all by inspection. We cannot figure out x-intercepts, but we can figure out the y-intercept because that is 0 and c. And c in this case is 6, so our y-intercept is 0 and 6. Just like all quadratics, except for those that have a special context, it's all real numbers. And again, we can't give the range because we don't know the y. So as you can tell, this one gives us less information. It gives us some information that the vertex form doesn't give us, but it's missing more pieces. And for the last one in factored form, we can't tell the vertex, but just like the other two, we have minus 0.5 down. We do know the max, that it has a max, sorry, but we would have to calculate the y, so we can't tell by inspection. We can tell, though, the x-intercepts. We know those, in this case, are -2 and 0, and the other one is 6 and 0. Remember, because the x-coordinate are the zeros of the function. They make it equal to 0. If you plug them in, the whole thing goes away to 0. And in this case here, we know the range. Let's write it in, the domain. Let's write it in interval notation. But we do not know the range of this one right here. Now, let's put that all together down in this little thing. I've actually left this in here for you. By inspection, I've written in here the things that vertex form tells us, and it's quite a bit. It's more than the other two. The things that are missing are the things that were blank. Same with standard deviation. I'm on a statistics mode today. In the standard form, we can determine concavity, y-intercept, domain. We cannot determine range. Who put that there? Oh yeah, I did. Let's get rid of that. Domain twice, don't need domain twice. Okay. And for concavity, for factored form, we can determine concavity, we can determine x-intercepts and the domain. So really, these two only differ in which intercepts they get. Now, what we don't know from inspection, we can calculate. We can calculate x-intercepts by figuring out, by making the function equal to 0 and solving for x, or we can make the x equal to 0 and solve for y. That happens not only down here for the x-intercepts, but again, down here we can use the same strategy up here for the y. Remember that for this one right here, to use the x equals, I'm just going to pull out my pointer, it's not working well. We can use x equals -2b over a, and again, oh no, that one I wrote down right. X equals -2b over a. We can use this to find the axis of symmetry, and then we can use this to value to solve y equals max or min. And we would do that by actually plugging in -2b over a over f. For the x-intercepts, again, same as above, and we can use the calculated max and min and concavity once we've determined these two things here to solve for the range. For factored form, we can actually expand it and simplify to standard form and then use the above to find those things that we calculated. And I realized there is one thing that we could do to find that, and in factored form, we can use x equals, and I'm going to put r plus s in brackets here, over 2. Remember, that's the average, and that gives us the axis of symmetry, and then we can use that to find a corresponding y value. And now the time is to practice. Try as many of these questions as you can. Well, that's the end of the video. If you have any questions about anything you see here or in the practice work, make sure you get in touch. I hope you have a great rest of your day. Take care.